Hello, everybody. Today we're going to talk about topic 6.1, accumulation of change. Today is going to be the first lesson that's going to lead us toward integration. So we're going to start with areas under the curve. So we want to talk about, when I refer to the area under the curve, I'm referring to the region between the function and the x-axis. Okay, we're always going to find that area between the function and the x-axis. Oops. So if I were to take a look at this first graph here, okay, and I were to shade in, let's say from 0 to, what do we got here? 2, 3, 4, 5, from 0 to 5. If I were to shade in the area under the curve, that means I'm referring to this region right here. Okay, now sometimes those regions can be below the x-axis as well. So if I do the same region from 0 to 5, right, I am referring to this region from 0 to 5. Okay, and then lastly, sometimes you have a part of your function above or below the x-axis. So from 0 to 5, I would have a section above the x-axis and then a section below the x-axis. Okay, so again, just for communication purposes, when I refer to the area under the curve, I'm always referring to the area between the function and the x-axis. Okay, so now here's kind of a little application problem, something that's fairly relatable to you guys. If you're on a road trip and you put the car on cruise control for 4 hours, you're traveling at 60 miles per hour, how far have you traveled? And I think most of you know distance equals rate times time, right? So if I'm traveling 60 miles per hour times 4 hours, that's going to give me 240 miles. However, I want to show you visually what that looks like. I can find the area under the curve from 0 to 4. And if you notice that this region is just a big rectangle, and the side of my rectangle, oops, I was going to write 60 there, not 60. The top part of my rectangle is 4 units long, or 4 hours long. And the height of my rectangle is going to be 60 miles per hour the whole time. It's constant. So if you find the area of that rectangle, you also get 240 miles. Okay. So there's a big idea that I want to use for this problem. So when you're finding the units for the area under the curve, the dependent unit, or the y variable, is going to be multiplied by the independent unit. So in other words, the unit for y, I'm going to put a y in here, times the unit for x. Okay, that's kind of the idea. So I'm going to take whatever the unit of the output is and multiply it by the unit of the input, which kind of makes sense. If you look at the example, if I take 60 miles per hour and I'm going to multiply it by my x values of 4, that's going to give me 240 miles. And you can even see the unit analysis here. If I did miles per hour times hours, okay, the hours would cancel and I would be left with just miles. Okay, so we want to make sure we always have the correct units. So take a look at this graph. It says the graph below represents the rate at which water is leaking out of a tank. You're going to see a lot of problems that deal with water leaking out. I guess it's just an easy application for people to use. The units are given in the graph. How much water has leaked out of the tank after 9 minutes? So what I want to do is I want to find the area under this curve, because this is a rate of change, right? So if I want to know how much water has leaked out, if you were to do gallons per minute times minutes, that would just give you gallons. So I'm just going to find the area under this curve, and I'm going to kind of break this up into chunks to make it easier on myself. So I have a little square here. So I'm going to say 2 times 2, right? Gives me 4 gallons. And then I have a little semicircle, right, on top here. Now the radius of that circle looks to be 2. So I'm going to do pi times 2 squared, which gives me 4 pi gallons. Now I'm going to have this little rectangle underneath. And that rectangle is going to be 4 units wide and 2 units tall. So it's 4 by 2, which gives me 8 gallons. And then last but not least, I need another color. Let's go with pink. I have a triangle, a right triangle, so 1/2 base, so from 6, and it's actually going to go all the way to 9. So the base is 3, the height is 2, which gives me 3 gallons. So now if I total this all up, I get 11, 15 plus 4 pi gallons of water. Okay, so that is how much water has flown through the pipe during those 9 minutes, or has leaked out of the tank, I should say, during those 9 minutes. Okay, so let's do it again, same idea. But instead of talking about water flowing out of a pipe, we're talking about movement, right? So a particle is moving along the x-axis at a rate by r of t, right? So this is really a velocity function, right? Centimeters per second. This is a velocity. I want to know how far the particle, how far is the particle from its starting position after 10 seconds? So if you were to take centimeters per second, right, the unit of the y value, times the unit of the x value, centimeters per second times seconds just gives me centimeters. That would give me a displacement or a distance, right? So what I want to do is I'm going to sum up all these areas. So I have this triangle here. So I'm going to do 1/2. The base is 2. The height, you have to be careful with your units here, is 10. So I'm going to get 10 centimeters for that. Now, watch what happens down here. This is below the x-axis. Okay, so something interesting is going to happen here. So now I'm going like the other direction. My velocity is negative. So what's going to happen is I'm going to have 1/2 2 times a negative 10, which would give me a negative 10 centimeters. So I'm back to where I started, believe it or not. And then last but not least, oh, I should have probably gone a little further. No, let's do that. Let's go a little further. I went only to 4, but that triangle really goes to 5. So let's go back a step, but you can see what I'm about to do. So if I go to 5, right, let's do this whole triangle here. So I'm going to do 1/2 times, from 2 to 5 would be a base of 3, and the height of that triangle would be a negative 15. Okay, and if I do this, I'm going to get a negative 45 over 2 centimeters. You might call that a negative 22.5, right? Now I have a rectangle, so let's change colors here. We'll go to blue. Now this will also be negative because it's below the x-axis. So the width is 2. The height is a negative 15. So that would give me a negative 30. I don't really need an approximation symbol here. So it's just 30 centimeters. And last but, I have a couple more little areas here. I have this little sliver of a triangle, which will also be negative. So I'm going to say 1/2. The base is 1. The height is still a -15. So I get a -15 over 2, which is a -7.5. And then last but not least, I have this triangle at the end. 1/2, the base is 2, the height is 10, which would give me a 10. So I just want to add all this up. So if you were to do, I'm going to write it on the top here, 10. I'm going to add all the positives together first, plus 10, right? There were two triangles that were positive. And then I'm going to subtract 22.5. I'm going to subtract a 30. I'm going to subtract a 7.5, right? So let's see what that gives me here. 20 minus, let's see what we get. That's going to be minus 60, which would give me a -40 centimeters, I believe. So how far did it travel? Well, it traveled 40 centimeters in the negative direction, right? So if it's moving, the question 3 says it's moving along the x-axis, I traveled 40 centimeters to the left, is basically what it's saying, okay? How far is the particle from its position at 2? At t equals 2 after 8 seconds. So what I want to do for part B, I'm just going to go back. And I'm just going to find the area from 2 to 8. So I just want to know this area, right? And this is what 2 sections here. Maybe I should color code that, okay? Which we kind of already found. This triangle down here was a -22.5. And then this rectangle was a -30. Oh, and we had this little sliver, which was a -7.5. So this was a -60 centimeters. It was the whole part that was negative. So from 2 to 8, I know that the particle traveled 60 centimeters to the left. Okay. Let's take a look at number 1 here, just more practice. All right. If I give you this graph, how many people are in the museum after 5 hours? Well, this is people per hour, right? Oh, let's take a look at your units. People per hour, and my x value is number of hours. So if I multiply that together, I get number of people. So I'm looking for an area under the curve. So after 5 hours really means I'm looking for, I'll try to color code these two areas, right? And I kind of break it up using, some geometric shapes that I'm familiar with. So I have a rectangle that is 4 and the height of 100, which gives me 400 people. And then you have this little sliver of a triangle, which is 1/2, the base is 1, the height is 100, which gives me 50 people. So if I total that all up during the first 5 hours, after 5 hours, I have 450 people have entered the museum or in the museum. Okay. Now, if I do the same thing for 10 hours, I'm just going to add, I'm going to take this 450 that I already have, and I'm going to add in the next places. Now, I should rephrase that. I'm not really going to add in, but I'm going to subtract, right? Because it's below the x-axis. So I'm going to say I have a 1/2, my base is 2, and then my height is going to be a -100, right? And if I do that, we'll simplify at the end here, okay? But if I keep going, I have a rectangle or a square that has a width of 2, a height of a -100, and then last but not least, I have a little triangle, width of 1, height of a negative 100. So let's put this all together. So I have 450, and then I'm going to say, what's that going to be? Minus 100, minus 200, and then minus 50. So I'm going to get 450 minus 350, which would be 100 people. Okay? So that would be the area under the curve. That would give me how many people are in after 10 hours. So let's keep going. So here's another particle motion. It kind of flip-flop back and forth. So where's a particle after 2 minutes, right? So I want this area for the first 2 minutes. So I have a little square and a little triangle. So if I do the square, I'm going to have 1 by 1. And the triangle, which is 1/2, 1 by 1, which should be 0.5. So in this case, where is it after 2 minutes? 1.5, and we need a unit here, meters. Okay. And then let's do part B. Where's the particle after 6 minutes? Well, I'm going to take the answer to my previous question, right, the 1.5, and I want to subtract off all these other little areas. Oh, I went a little too far. I only wanted to go to 6 minutes. So let me go back. I'm going to just do this little square here. And I have actually a little quarter circle. I want to combine all of those together. So let's take the 1.5 from the previous part, and then we're going to add a 1/2, the base, which is 2, the height. So I'm doing the purple one right now. Maybe I should do this in purple. 2, and then the height is -2. And then the green section would be a 2 by -2. And then the blue section is a quarter of a circle. So I'm going to do pi times the radius squared, which the radius is 2 over 4. But we need to make sure it's negative because it's below the x-axis, right? So we're going to subtract off anything that's below the x-axis. So I have 1.5 minus 2 minus 4, and then last but not least, minus pi. So if I combine this all together, I'm going to get a negative 4.5 minus pi. So then where's the particle after 10 minutes, right? So we're going to do the rest of this. So if I were to put this quarter circle on, I'm pretty sure that this would also be a negative pi. This square would also be a -4. But I have a little triangle there that I'm going to have to figure out. So this triangle, 1/2 base times height, right, would be a -1. And then last but not least, this little triangle, which would be a 1/2 base times height. 1/2, 1 times 1 is just 1/2. So let's add this all up. Let's get the whole thing. So if I take my previous answer, -4.5 minus pi, and then I'm going to subtract another pi. I'm going to subtract a 4. I'm going to subtract a 1, and I'm going to add a 1/2. So if I do that, I get, let's see, -9, correct me if I'm wrong there, minus 2 pi. Get something like that, okay? Which ultimately means that's how far in the, because again, the question is moving along the x-axis. I moved that distance to the left, right? Because I started at the origin. You notice I started at the origin. So then I went that far to the left, okay? All right. So if I keep going here, the amount of water in a small pond is changing at a rate modeled in the graph below, where the rate is measured in cubic inches per hour. How much water has been gained or lost during the first 3 hours? So again, you can see it's below the x-axis, so it's going to be lost for sure. Let's just kind of, I'm going to write in some amounts here. So this rectangle is a 2 by 3, so it's going to be -6. Again, it's negative because it's below. I have a 1/2 base times height, which would give me a negative, I'm going to draw a little arrow here, negative 1.5, because the base is 1, the height is -3. Then I only want from 0 to 3, perfect. So this answer would be a -7.5 inches cubed. Right? Always make sure we have the correct unit on our answer. Now, if I want to do for all 12 or 10 hours, okay, then we just keep going with the process, right? But these will all be positive values. So I have a little, same sliver actually. This would be a positive 1.5. I have a little interesting shape here. Probably the best way to approach this shape would be to take this whole rectangle and then remove the semicircle. So I'm going to take this whole rectangle, which is a 2 by 3, and then I'm going to subtract a semicircle, which would be pi r squared, or just pi times 1 squared. And I want a semicircle, so I'm going to divide it by 2. So I get a 6 minus pi over 2 for this little area here. And then if I keep going, I have a big rectangular square in this case, which would be 3 by 3, which would be 9. And then last but not least, I have a sliver, which would be a positive 3 over 2, or 1.5, right? So let's add it all up. So I have the negative 7.5 from part A. Then I'm going to add to 1.5, so I'm just going to call that 3, right? I'm going to add 1.5 for the triangle in the beginning, the triangle at the end. So that's 3. And then I'm going to add a 9, and I'm going to add a 6 minus pi over 2. So if I do that, I have 12 minus 7.5, which would be a 4.5, plus 6 minus pi over 2, or a 10.5 minus pi over 2, which would be how much water was, in this case, that would be gained after 10 hours. Okay? So 4, 5, and 6 don't ask you to calculate. They just want you to know what are the units for the area under the curve. So if f of t is measured in milligrams per year and t is in years, again, I'm going to take the y value times the x value. In this case, I'm going to take f of t times t. So if you were to take milligrams per year and you multiply it by years, you just get milligrams, right? G of t is measured in gallons per month. T is in months. So if you take gallons per month times months, you just get gallons. Okay. Last but not least, H of t is measured in feet per hour times hours, which gives me feet. Okay. And then there's a couple just little test. There's one little test prep question right here. Which of the following best approximates the total number of gallons of water passed through the garden hose on that day? Now, if you notice that this is a curve, it looks very much like a sine or a cosine function. We're going to investigate this problem a little bit more in topic 6.2. We're going to talk about Riemann sums. So again, hopefully this helped. Accumulating the areas under the curve is the first step to integration, and there'll be a practice to follow.